morning everyone, hope you all safe with a good health. With you Ms. Dina Al-Badri, a science teacher for grade 8. Today we will start lesson 2, properties of the wave. How can we describe a wave? We said last time the wave has amplitude, has a wavelength, has a frequency. So a wave's amplitude is measured of how far the particle in the medium move away from their normal rest position. And what is the meaning of the wave? Is a disturbance that transfers energy from one place to another place. So the wave speed difference according to the speed, according to the amount of energy that carried by the wave. What is the wavelength? It's the distance from any point on a wave to an identical point on the next wave. This measures the length of one cycle or repetition. What is the wavelength of this wave? What is the wave's amplitude? The wavelength, it will be the distance between crest and crest, or the distance between crest, trough and trough, two identical points. So what is the difference between amplitude? So here what is the distance, what is the wavelength? It is the distance between this point and this point, or the distance between this point and this point. Okay, but the amplitude, it will be the distance between trough and crest. Okay. Another property for the wave is the wave period. It is the time required for the wavelength to pass a given point. Okay, so the time required for one wave to pass a given point is called the wave period. And what is the frequency of the wave? How many cycles occur in an amount of time. Okay, this time usually it will be 1 second. So our measurement is related to the time. The time will be 1 second. Okay, the frequency is the wave. Tells how many cycles occur in an amount of time, usually 1 second. Frequency is measured in hertz. What is the measuring unit for the frequency? Hertz. For the wave period, a second. For the wavelength, meter. 1 hertz equal 1 wavelength per second. Frequency is the inverse of period. What affects the energy of a wave? Some waves carry more energy than others. For a mechanical wave, amplitude is related to the amount of energy the wave carries. For two similar waves, the wave with greater amplitude carries more energy. Greater frequency also mean greater energy in a given amount of time. For most electromagnetic wave, energy is most strong related to the frequency. So when the wave carries more energy, carries more mechanical wave, it means carries more energy, carries more amplitude and more frequency. Okay.
Welcome back. Once again, we're going to use our PhET simulation to look at the relationship between frequency and wavelength and see if frequency and wavelength affect the velocity of the wave at all. You might be surprised by some of the results. First of all, we'll start by oscillating the end. Again, we're creating a transverse wave. We can see that the disturbance is perpendicular to the direction the wave is traveling. And once again, we'll turn off the damping. So we don't want any friction to be occurring. We want a nice clean wave that we can study easily that's traveling through a window. Again, we choose the window so that it does not reflect and come back on itself. We just want to look at the effects that frequency has on wavelength. So up top you see a slider that gives us our controls over frequency. I can turn it to low frequency or high frequency. You can ignore the number. The number 50 does not mean 50 hertz. 50 hertz would mean that the wave is being created 50 times per second, and clearly that's not true. In this simulation, the 50 just represents the fact that it's at 50% capacity. That would be 100% capacity up at this end. So we can adjust the frequency of the oscillations by moving that slider. So let's start with a low frequency wave. And we can see right away when I create a nice low frequency wave, very few waves per second, the wavelength is quite long. And if I create a higher frequency wave, more waves per second, it in turn creates shorter waves. The wavelength gets smaller. Now, if I choose a frequency of, let's pick 20. Okay, so there's a frequency of 20, and I'm going to pause it. I'll step it through so we see one full wave, two crests. Now I'll grab a ruler, and with a frequency of 20, from crest to crest is one wavelength, and we can see that it's roughly 80 centimeters. From here to here is roughly 80 centimeters. Now let's take our frequency and double it. Let's bring it up to 40 and see what happens. Okay, so I've doubled the frequency. And again, I'll pause it and measure from crest to crest. And we can see that our wavelength is now 40. So doubling the frequency has halved the wavelength. It seems to be an inverse relation that's occurring there. Now, if I double the frequency and half the wavelength, since velocity is frequency times wavelength, the effect of one is being countered by an inverse effect on the other variable. So in other words, doubling f means halving the lambda, the wavelength. So that would make the velocity constant. We can see from this sim that this is in fact the case. If I run the sim at a fairly high frequency, so let's bring it up to 80, we're making many waves per second, and then suddenly slow it down. Here, I'll speed it up again, and slow it down, speed it up, slow it down. Notice that the speed at which those crests are traveling does not change. If it did change, these higher frequency waves would actually catch up to the lower frequency waves. And it doesn't happen. They stay the same distance away from those lower frequency crests. So the velocity of the wave is independent of f and lambda. In fact, the only way you can change the velocity of a mechanical wave is to change the medium itself. And to do that on this simulation, we'd have to change the tension. And we can see right away, when I drop the tension a notch, now the waves are slower. Again, the effect of frequency and wavelength is inversely related to each other, but the only way I can change the actual speed of the wave is to change the medium's tension. Change the medium. Here we are, even a lower setting, and we can see it's moving even slower. It gets a little bit distorted. Drop it down so we can actually see the wave here. So now it's moving quite slow. What happens if I drop it down even lower in tension? Right? It's even slower. And if I crank the tension up, we get back to our fast wave again. Notice the wavelength elongates. So the velocity of the wave is independent of f and lambda, even though it suggests that it's dependent on the equation. Velocity is constant unless the medium changes. Frequency and wavelength are inversely related to each other.